Hey everyone, Mr. Fott here. Today's lecture is going to be on the chemical context of life. First up are the must-knows, the three subatomic particles and their significance, and the types of chemical bonds, how they are formed, as well as their relative strength compared to each other. First up, we have matter. Matter has mass and takes up space, is affected by gravity, and consists of both elements and compounds. In short, what matter is anything that is tangible and physically exists that is within our grasps here. On the other hand, energy. Energy is what moves matter. There are two different kinds, as we will be talking about, potential versus kinetic. Energy, by definition, is the ability to do work. It helps us do conversions into various types of conversions, as well as can be measured in the context of sound, light, and heat. Other things that we want to differentiate here are elements versus compounds. Elements, you may recall from chemistry course, are pure substances. They cannot be broken down by ordinary means into any other substances, in part because they are just purely one element, thus the title of elements. Whereas on the flip side here, compounds, they are made up of two or more different elements, and they are combined together into fixed ratios. So some examples of this would be H2O and CO2, versus our elements, just H for hydrogen gas and just N for nitrogen gas. So we have elements versus compounds. Elements of life, again, you may recall from standard biology, there are 25 major elements of life, both major and minor elements here. About 96% of all living forms are going to be made up of just four elements, however: oxygen, carbon, hydrogen, and nitrogen. Less than 4% is going to be made up of phosphorus, sulfur, calcium, potassium, and other trace elements such as iron and iodine. Now you can remember this. There is a few different mnemonic devices. I always like ponchos, Ponchos. So the six major elements of life, as you may recall here, is phosphorus, oxygen, nitrogen, carbon, hydrogen, oxygen again, which has a reason behind that, as well as sulfur. If we continue on and we're to break down, let's say, a human body into its elements here by relative percentage, we can see that the 96% is made up of, again, those four elements. But notice how oxygen has way more of any of these other elements here. Thus, in the acronym ponchos, it's a great and little analogy here because the oxygen has more of it. Just a little reminder there. But if we break it down again, the less than 4% is made up of the other elements: calcium, phosphorus, potassium, sulfur, sodium, and chlorine, as well as magnesium. There are, of course, less than 0.01% are going to be all these other elements here, a slew of them. Other notable ones: iron, iodine, copper, cobalt, zinc, molybdenum, selenium, silicon, and so on. So those are going to be very minor in the grand scheme of things, but basically the bulk of us are made up of those four elements with a little bit extra thrown in there as well. Atomic structure, just to refresh your memory here, that atoms are the smallest unit of matter and retains their properties of a given element here. Atoms are made up of three subatomic particles. We have protons, neutrons, and electrons. The mass: protons and neutrons have an AMU, or atomic mass unit, of 1. The electrons are basically circulating balls of energy in which their mass is negligible. It's practically zero. The location of them: protons and neutrons are located in the center or the core, known as the nucleus, whereas the electrons are floating around the outside into various orbitals or shells. The charges: neutrons are neutral with a charge of 0, protons are positive with a +1 charge, and electrons are negative with a -1 charge. Isotopes are another type of structure that you may recall from standard chemistry here. This is where the number of neutrons are going to then change. Protons are not going to be altered. If you recall on how we change elements or into ions and isotopes is varying degrees of neutrons, whereas the protons and the electrons are not going to be touched. Isotopes are going to make their way into AP biology from time to time. Basically, what they are going to act as is what are called radioactive isotope tracers. These are mostly used in medical diagnoses, and they can follow different molecules based on what isotope they happen to be injecting the person with. And we'll talk about those when those examples happen to come up. Chemical bonds, there are a few of them that we are going to hit on. So first up, we're going to talk about covalent bond. That prefix co means together. So these electrons here, again, keep in mind, bonds are all about the electrons. And in this case, they're going to be shared. Thus that prefix co meaning together. So these electrons are working together to hold the structure together. There are two different varieties of covalent. We can either have something be what's called polar covalent or non-polar covalent. Basically, think about it as a tug of war. That if we're going to have something that is winning in the tug of war, whereas one side is losing in the tug of war, this is known as a polar bond. Versus if they are going to be perfectly equally shared, then it would be a non-polar covalent bond. So the example that we have is HCl, so hydrochloric acid. The chlorine seems to be winning the tug of war. They are still sharing the electrons. However, one side is going to be slightly more negative than the other. Versus in the bottom portion here is our nonpolar covalent, in which the two hydrogen atoms are equally sharing. Nobody's winning in the tug of war here. Second type of bond that we're going to talk about are ionic bonds. This is, as the name suggests, where we have multiple ions here. Specifically, there are going to be two, one of which is going to be a positive and one of which is going to be a negative. Some of these elements are going to be givers, which means they're going to be donating the electrons, and others are going to be takers. They will be receiving the electrons. A great example would be sodium chloride, a little bit of NaCl. Another easy way to identify whether something is going to form an ionic or covalent bond are identifying them as metals and nonmetals. Remember the staircase. That's an easy way to know which ones are metals versus non-metals. These are going to be things that are going to be affected by the environment. So things like water, for instance, as we're going to talk about later in this unit, is going to play a huge factor into all of this. So ionic bonds are huge. Keep in mind that ionic bonds, they are taken, they are not shared. So somebody is going to be giving and somebody is going to be losing. Next type of bond that we're going to spend some time focusing on are what's known as hydrogen bonds. So these hydrogens basically of polar covalence. So this is only going to exist within polar covalent molecules here. They're going to be attracted to the electronegative side or the more slightly negative portion of it. There are going to be three major elements that we're going to focus on in which we're going to identify where hydrogen bonding might occur. Basically those three, there's two of them in this example here. We can see the hydrogen bond between water and ammonia. The hydrogen bond, the hydrogen seems to be bonding right here in the middle, you can kind of see. So there is what's called the delta symbol. That's this funky looking symbol right here. This is known as delta. That is it's a Greek letter. It's like the lowercase letter d, basically, something equivalent to our alphabet. And it just means slightly or just a little. So this means slightly. That's what that really means. And so when we're looking at this context, we see delta positive, delta negative. It means just a little positive, a little negative. This is not a formal full charge. This is only a partial charge or slightly charged. But what we see here is that this hydrogen is attracted to the nitrogen. That is one of our first elements. There are three of them in general, biologically speaking, in which are going to form hydrogen bonds. Nitrogen is one of them. Oxygen is the second one. Again, if we notice, we can see that oxygen has that slightly negative charge. All of our hydrogens are going to have slightly positive charges or delta H's or delta positives here when we're taking a look at them and looking at their polarity here. The third element that is not identified here and is not quite as popular in the biological context but occasionally shows up is F. Or fluorine here. There's a fourth one that technically exists but comes in only on rare occasions, which is sulfur. But for the most part, the nitrogens and the oxygens are basically going to dominate the entire thing. Next up, we have what are known as van der Waals. Oh, geez, I'm sorry. Let me erase all this. So we have van der Waals forces. This is a slight force, so this is actually working in decreasing strength. Van der Waals are going to be the least strength. Basically what these are two atoms as they are going to be physically attracted to one another. This is not by charge, whether it be full charge or partial charge. There are no charges going on here. There's no sharing of the electrons. It's basically just very weak interactions between molecules. We will not be focusing so much on van der Waals. I would not put a lot of emphasis on this one, to be honest. So, of our different types of bonds, these are the three that we should be focusing on: ionic, covalent, and hydrogen. All of them are going to be important to life. Notice how we left out the van der Waals, albeit it does exist here. But breaking it down into the different categories here, covalent bonds, these are going to be the strongest of the bonds here. It's going to form basically most of the molecules that are going to be existing within life forms here. Ionic bonds are going to be like next up in line. These are going to be quick reactions here and quick responses. They're basically going to be involved in a lot of chemical reactions, as well as hydrogen bonds. These are even weaker, and then at this point here, they're going to be bonding to our electronegative atoms again, the nitrogen, the oxygen, and the fluorine. A very rare occasion, the sulfur, but not so much here. All of these are going to be made and broken within our chemical reactions as we will be discussing them biologically speaking. So why are we talking about these molecules and bonds and all of this stuff? Is that all of this is going to affect a molecule's shape. This is a big theme in AP Bio here. Shape is going to determine function. And if things are shaped similarly, so like for instance, we have an example called natural endorphins. So this is that feel-good drug. Maybe you did something really great, really accomplishing, and you get that like surge of energy. That would be your endorphins releasing the feel-good drug or the happy drug here. Morphine, notice how we have similar shapes right here. They do similar functions. So when we have things that are of this nature, this is basically what medicine is about. It's about mimicking things that are naturally occurring within our body here, and then we can go ahead and take them in various forms, be it pills, injections, or whichever else. So the shapes of these molecules, which are determined by the bonds, which ultimately are going to affect their function here. Things that are similar are going to mimic one another. So even though we use morphine would be a drug which is synthesized in a lab, it's going to mimic endorphins, which is why the two of these can be used kind of synonymously here. Other cells or other types that we're going to then see is how these play out within these giant blobs. And get used to me saying this a lot. These giant blobs, usually purple or blue or kind of somewhere around there, are going to be proteins. So each one of these are going to fit similarly. This is why that their shape is determining their function, basically how they are going to attach to these receptors within our body. So that's the big takeaway from here. Shape determines function. Another major theme that we're going to be talking about as we go through this unit is talking about hydrophilic and hydrophobic. Hydro is referring to water. Philic or phobic, phile means attracted to or liking of, whereas phobia or phobic here is referring to a fear. So what is going to be attracted to water versus what is going to be fearing of water or wants to move away from water. And so we have two different categories. Things that are ionic, they are charged. And as we said, with water, water is a polar molecule, and it has a slightly positive and a slightly negative end. It can form those hydrogen bonds. So it does a really good job interacting with ionic compounds or other polar covalent compounds as well. Whereas the covalent ones are more hydrophobic. These are non-polar specifically. These are no charges, absolutely not. So things like oils and fats, for instance, are really great examples. So thank you all for listening. Let me know if you happen to have any questions. Thanks a lot.